So after applying the proposition in a few examples, now we are in a position to prove this proposition. So note that the proposition says a set of states is closed, C is closed if and only if take any I in C and any J in C complement, then the one-step transition probability is 0. And as I said, it's very useful because you just need to look at the transition matrix, that's all. You don't even have to compute its power. Okay? Just from looking at the transition matrix, you'll be able to verify whether a given set is closed or not. Okay, so how do you prove it? So let's first prove the necessity. So that is the only if part in this case. So we'll again, in this case, prove the contrapositive statement of the necessity. So namely, we have to show this, we have to show that if C is closed, then Pij is equal to 0 whenever I is taken from C and J is taken from C complement. Instead of that, we'll show the following. Suppose there exists I and J, I in C and C in J complement such that Pij is strictly positive. We will show that C is not closed. We'll start with the set C, subset of S, okay, and then we assume that there exists I in C and J in C complement such that Pij is strictly positive, and we'll just show that C is not closed. That will prove the only if part of this proposition. To do that, first observe that since we have, we have taken an I in C and J in C complement, so C is in J is in C complement. So therefore, the set of all n non-negative integers n such that xn is equal to j is actually contained in the set of all non-negative integers n such that xn is in C complement. This is because if xn is equal to j, it's already in C complement. So this event implies this event. So therefore, this is contained in this. Because j is in C complement. Now we know that a bigger set has smaller infimum. If you have two sets, the set which is bigger will have smaller infimum. So therefore, this is the bigger set, this will have the smaller infimum. So the infimum will just reverse this order. And this infimum of the first set is just tau j, that the first time the Markov chain is going to hit j. And an infimum of the second set is just tau C complement, that the first time the Markov chain is going to hit C complement. So what this says is that tau j is therefore an upper bound for tau C complement. And this is also obvious in the sense that if you have already hit j, then you have definitely hit C complement by that time or a time before, because, okay, you may have hit some other state in C complement instead of j, and then you may have hit C complement. So therefore, tau j is a trivial upper bound for tau C complement. Okay. Now, once we have this upper bound, then it's very easy to see what's going on to show that C is closed. We know that the way we have taken this, Pij is positive, which implies by the proposition that I leads to J. I leads to J is same as saying, starting from I, tau j is finite with positive probability. Now we know that tau j is an upper bound for tau C complement. So tau C complement is an even smaller random variable. So therefore, tau C complement is also going to be finite with positive probability. Okay, so starting from I, tau C complement is finite. This event is going to be contained in this event. That's because This event is going to imply this event because tau c complement is bounded by tau j. So if tau c complement is finite, tau j is also going to be finite. Okay. Sorry, so I made a mistake here. This event is contained in this event. Sorry. So this is the bigger random variable. So if tau j is finite, then tau c complement has to be finite. The other way around may not be true. Sorry. So tau j is the bigger random variable. If you know tau j is finite, then tau c complement has to be finite. So therefore, this event is contained in this event. So therefore, this probability starting from I is definitely less than equal to this probability. So this probability is less than equal to this probability. So therefore, this probability is bigger than equal to this probability. And we already know, because I leads to j, this probability is strictly positive. Therefore, starting from I, you will hit C complement in a finite time with positive probability, which says that C is not closed. But if C is closed, this particular thing has to be infinite with probability 1. So therefore, C is not closed. So this proves the only if part. The proof is actually very easy. I mean, I've written all the details, that's why it looks longer, but it just says that since J is not in C complement, tau J is a trivial upper bound for tau C complement. Because if you have already hit J, you must have hit C complement. And then also I leads to J, so therefore tau J is finite with positive probability, and therefore something smaller is also going to be finite with positive probability. And that's it. That shows C is closed. Now let's prove the sufficiency, namely the if part. So let's assume that for all I in C and for all j in C complement, Pij is equal to 0. You have to show that C is closed. Take I in C. Now recall what is tau of C complement. We just used it, but let's just recall it. It's just by definition, it's just the first time xn, which is C complement. Now, n equal to 0 is also allowed, so we have to keep that in mind. But in this case, it doesn't matter if you start with a state in I, which is in C. So if I is in C, then I is definitely not in C complement. This is saying a double negative, right? I is in C, therefore I is not in C complement. Therefore, there is no way this can be 0. Now C complement will be 0 only when x0 is in C complement. But if you start at I, which is not in C complement, x0 can never be in C complement because x0 is I, you're starting from I. So therefore, this hitting time of C complement cannot be 0. So it can be 0 with probability 0. Okay? Also, this hitting time cannot even be equal to 1. Why? Starting from I, of course. So starting from I, which is not in C complement, this hitting time of C complement cannot be 1. Why? Because this probability, starting from I of T of C complement equal to 1, is just the probability that x1 is in C complement. x0 is, of course, I, which is not in C complement, but then x1 has to be in C complement. That's the only way this can be 1. Okay? This infimum can be 1. Now, what is the probability starting from I of x1 is in C complement? That's the sum of all j's in C complement of Pij. Now, each of these Pij is 0 because of the hypothesis of the theorem. Okay? So, therefore, this sum is 0. And hence, this cannot be 1 as well. Now, moreover, for any integer bigger than or equal to 2, Pi cannot be n as well. Tau C complement cannot be n as well for a Markov chain starting from I. Why? So let's compute the probability Pi of tau C complement is equal to n. What does it mean? It means the Markov chain starting from I, which is not in C complement, we know that already, which is in C. It has to remain in C up to time n minus 1. And then it has to go outside C at the time n. That's the only way the heating time of C complement can be n. So starting from I, x1 has to be in C, x2 has to be in C, all the way up to xn minus 1 has to be in C, but xn has to be in C complement. That's the only way this would be equal to n. Now we have computed such probabilities many times. This is just the sum of all different ways of this can happen. So this can happen if you go from I to some I1, which is in C at the time 1, then from I1 you go to some I2, which is in C again, all the way up to In minus 1, which is in C. And finally, you reach a state J from In minus 1, which is in C complement. So therefore, this probability is just the sum of all this product of the transition probabilities. Now note that in the sum, what is important is that the last one, in the last quantity in this sum is In minus 1 is running over C. So In minus 1 is in C and J is in C complement. So therefore, this probability by hypothesis is going to be 0. So this is 0. So therefore, all the terms would become 0. And therefore, this probability would be 0. We have just calculated this term longhand, this probability longhand. So what this shows, therefore, is that for every n, for every non-negative integer n, starting from I, which is in C complement, which is in C, sorry, you reach C complement first time at the time n, this probability is 0 using the hypothesis that Pij is equal to 0 for all I in C and Ij in C complement. So therefore, starting from I, you will be able to actually reach C complement in a finite amount of time. This probability is nothing but, as you can see, is the limit n going to infinity starting from I, tau of C complement is less than or equal to n. Of course, because these events are increasing and they increase to this event here. So therefore, this probability is increased to this probability. Now note that this probability is nothing but this sum. Is the sum of tau of C complement equal to n, where n runs from 0 to n. Now note that each of this term here is actually 0. We have just proved it. When n equal to 0, it's 0. When n equal to 1, it's 0. N equal to 2, it's 0. N equal to 3, it's 0. All of them, it's 0. So therefore, all of the terms here is actually 0. And therefore, this entire sum is 0. Therefore, the limit is also 0. Which shows that C is closed. Because the heating time of C complement starting from a state in C has to be infinite with probability 1. Okay, so this completes the proof of this proposition. We'll now learn something called dissection principle. Now, to be honest, we are going to learn it in the next class, but I'm just giving a prelude of what is going to come. So far, we have decomposed the state space. We are now going to decompose the Markov chain itself. So the Markov chain is what? X0, X1, X2, and so on, right? We are going to decompose this Markov chain evolution into parts, into independent and identically distributed blocks. Okay? That the blocks will consist of pieces of path between consecutive visits to a fixed state. So you'll start with a state, say. First time you come back to that state, you observe the Markov chain up to that point. That will be your first block. Again, you're back at this state. You start from there and then come back to this state. That will be your second block, and so on. We'll show that these blocks are going to be IID. Okay? Now, it would be useful to think of the process as these IID pieces knitted together. Now, this is obviously now extremely vague. We'll make it clear next time. In particular, once you have IID structure in the system, you will be able to invoke, say, laws of large numbers, central limit theorem, etc. In this course, we won't actually apply the central limit theorem, but we'll definitely apply the laws of large numbers, the strong law of large numbers. This also has another name. It's called regeneration. So that Markov chain, whenever it starts, it comes back to that point, and then it sort of regenerates. It's whatever happened is sort of whatever is going to happen in future is going to be independent of whatever happens so far. And this is pure Markov property, as you can see. Okay? So we'll formalize it next time, and I'll tell you what exactly I mean by dissection principle. Let me stop here.